Section 1.2.5. Back to neural networks. Around 2010, although neural networks were almost completely shunned by the scientific community at large, a number of people still working on neural networks started to make important breakthroughs. The groups of Geoffrey Hinton at the University of Toronto, Yoshua Bengio at the University of Montreal, Yann LeCun at New York University, and IDSIA in Switzerland. In 2011, Dan Sirasan from IDSIA began to win academic image classification competitions with GPU-trained deep neural networks, the first practical success of modern deep learning. But the watershed moment came in 2012 with the entry of Hinton groups in the yearly Large-Scale Image Classification Challenge, ImageNet. ImageNet Large-Scale Visual Recognition Challenge, or ILSVRC for short. The ImageNet challenge was notoriously difficult at the time, consisting of classifying high-resolution color images into 1,000 different categories after training on 1.4 million images. In 2011, the top 5 accuracy of the winning model, based on classical approaches to computer vision, was only 74.3%. Then, in 2012, a team led by Alex Krzyzewski and advised by Geoffrey Hinton was able to achieve a top 5 accuracy of 83.6%, a significant breakthrough. The competition has been dominated by deep convolution neural networks ever since. By 2015, the winner reached an accuracy of 96.4%, and the classification task on ImageNet was considered to be a completely solved problem. Footnote 5. Top 5 accuracy measures how often the model selects the correct answer as part of its top 5 guesses out of 1,000 possible answers in the case of ImageNet. Since 2012, deep convolution neural networks, or ConvNets, have become the go-to algorithm for all computer vision tasks. More generally, they work on all perceptual tasks. At any major computer vision conference after 2015, it was nearly impossible to find presentations that didn't involve ConvNets in some form. At the same time, deep learning has also found applications in many other types of problems, such as natural language processing. It has completely replaced SVMs and decision trees in a wide range of applications. For instance, for several years, the European Organization for Nuclear Research, CERN, used decision tree-based methods for analyzing particle data from the ATLAS detector at the Large Hadron Collider, or LHC. But CERN eventually switched to Keras-based deep neural networks due to their higher performance and ease of training on large datasets. Section 1.2.6. What makes deep learning different? The primary reason deep learning took off so quickly is that it offered better performance for many problems. But that's not the only reason. Deep learning also makes problem solving much easier because it completely automates what used to be the most crucial step in a machine learning workflow: feature engineering. Previous machine learning techniques, shallow learning, only involved transforming the input data into one or two successive representation spaces, usually via simple transformations such as high-dimensional nonlinear projections, SVMs, or decision trees. But the refined representations required by complex problems generally can't be attained by such techniques. As such, humans had to go to great lengths to make the initial input data more amenable to processing by these methods. They had to manually engineer good layers of representations for their data. This is called feature engineering. Deep learning, on the other hand, completely automates this step. With deep learning, you'll learn all features in one pass rather than having to engineer them yourself. This has greatly simplified machine learning workflows, often replacing sophisticated multi-stage pipelines with a single, simple, end-to-end deep learning model. You may ask if the crux of the issue is to have multiple successive layers of representations. Could shallow methods be applied repeatedly to emulate the effects of deep learning? In practice, successive application of shallow learning methods produce fast diminishing results because the optimal first representation layer in a 3-layer model isn't the optimal first layer in a 1-layer or 2-layer model. What is transformative about deep learning is that it allows a model to learn all layers of representation jointly at the same time, rather than in succession, greedily, as it's called. With joint feature learning, whenever the model adjusts one of its internal features, all other features that depend on it automatically adapt to the change without requiring human intervention. Everything is supervised by a single feedback signal. Every change in the model serves the end goal. This is much more powerful than greedily stacking shallow models because it allows for complex, abstract representations to be learned by breaking them down into long series of intermediate spaces, or layers. Each space is only a simple transformation away from the previous one. These are the two essential characteristics of how deep learning learns from data: the incremental, layer-by-layer way in which increasingly complex representations are developed, and the fact that these intermediate incremental representations are learned jointly, each layer being updated to follow both the representational needs of the layer above and the needs of the layer below. Together, these two properties have made deep learning vastly more successful than previous approaches to machine learning. Section 1.2.7. The Modern Machine Learning Landscape. A great way to get a sense of the current landscape of machine learning algorithms and tools is to look at machine learning competitions on Kaggle. Due to its highly competitive environment, some contests have thousands of entrants and million-dollar prizes, and to the wide variety of machine learning problems covered. Kaggle offers a realistic way to assess what works and what doesn't. So what kind of algorithm is reliably winning competitions? What tools do top entrants use? In early 2019, Kaggle ran a survey asking teams that ended in the top 5 of any competition since 2017 which primary software tool they had used in the competition. See Figure 1.12. It turns out that top teams tend to use either deep learning methods, most often via the Keras library, or gradient-boosted trees, most often via the LightGBM or XGBoost libraries. It's not just competition champions either. Kaggle also runs a yearly survey among machine learning and data science professionals worldwide. With tens of thousands of respondents, this survey is one of our most reliable sources about the state of the industry. Figure 1.13 shows the percentage of usage of different machine learning software frameworks. From 2016 to 2020, the entire machine learning and data science industry has been dominated by these two approaches: deep learning and gradient-boosted trees. Specifically, gradient-boosted trees is used for problems where structured data is available, whereas deep learning is used for perceptual problems such as image classification. Users of gradient-boosted trees tend to use scikit-learn, XGBoost, or LightGBM. Meanwhile, most practitioners of deep learning use Keras, often in combination with its parent framework, TensorFlow. The common point of these tools is that they're all Python libraries. Python is by far the most widely used language for machine learning and data science. These are the two techniques you should be the most familiar with in order to be successful in applied machine learning today: gradient-boosted trees for shallow learning problems and deep learning for perceptual problems. In technical terms, that means you'll need to be familiar with scikit-learn, XGBoost, and Keras, the three libraries that currently dominate Kaggle competitions. With this book in hand, you're already one big step closer.